typically, in 252, I would then use that equation, I would derive something, and I'd come at this next equation in the reverse order, but for you, we'll start with this thing known as Ampere's law.
I don't even know how you do 252 in the allotted time frame. I feel like it's everything we're doing plus a lot of calculus.
Yeah, well, by that time, all of them would have been, in 252, they all would have had at least 2 years of calculus, and most of them, half of them have had third year, and the other half are in their third year of calculus. So there's a lot of math that I can just skip steps on, so we save time there. Ampere's law. Ampere's law says that if I add up an infinite sum, or doesn't have to be infinite, if I add up a sum of B dot delta L, that is equal to mu naught I, now enclosed. So what I'm talking about here is that if I take some loop, now we've done Gaussian surfaces before where we've got this three-dimensional shape. This is just, I have a line that connects up with itself, and I add up the magnetic field all along it. So do the magnetic field for that segment, plus that segment, plus that segment, or, sorry, magnetic field times that length, plus magnetic field times that length, plus magnetic field times that length, and so on, all the way around. That will equal our constant here, our permeability of free space, times the current that's running through this loop. And when I say through the loop, I'm talking about if I have a wire that's, like, if these are wires right here, there's current flowing through the loop. Yes?
Is it current enclosed? Is that what the
Yes.
subscript is? Okay.
Yeah. Enclosed, encircled, encircled probably would be better wording.
Okay.
Can't believe I put it away yesterday. So if I hook this up to a power supply, so let's just pretend it's hooked up to a power supply, and I want to find the magnetic field around a particular loop there, I just imagine that there's a circle around here, and if I add the magnetic field times the length all along there, that will ultimately add up to mu naught times whatever current's flowing through the wire. Now, what does that have to do with you? Let's pretend we have an infinitely long wire. Goes on forever. And I have my current flowing this way. So I've got my long wire here, infinitely long. And what I'm going to do is I'm going to imagine a circle that's going around it. There's my circle. At this point, imagine that I've got this line going right through, I've got my wire running right down the middle. Now there is absolutely no reason why the magnetic field that's created would have a different magnitude here than it has down there, or there, or there. That the magnetic field, the magnitude of the magnetic field would be the same everywhere along this if that wire is running straight down through the middle. So since the magnitude of the magnetic field is the same, all I have to do is now just add up the magnetic field times the length everywhere on there. So I'd have, just pick some spot on the circle. I have B1 times delta L1 plus B2 times delta L2 plus B3 times delta L3, and so on. Well, if the magnitude of the magnetic field is the same everywhere, I can just factor it out. And I'm left with delta L1 plus delta L2 plus delta L3, and so on. And what is the sum of all the little lengths all the way around the circle?
The circumference?
And what's the formula?
2 pi r?
No, it's
Pi times
yeah,
d.
it's pi d.
Oh,
Right.
yeah. let's,
pi d or 2 pi r.
let's do the 2 pi r for now. So what I have here is that if my radius of my circle here is r, then what I end up with is the magnitude of my magnetic field times 2 pi r is equal to mu naught times the current running through the wire. And so the magnitude of my magnetic field is equal to mu naught I over 2 pi r. This is the magnetic field, the magnitude of the magnetic field created by a current a distance r away.
So it's like divided by circumference.
Exactly, yes.
Wait, could you say that sentence one more time? This is the magnitude of the magnetic field created by.
A current at a point a distance r away from the wire. There's another aspect to this formula which has some importance. We had Gauss's law of electricity. The fact that the electric flux through a closed surface, which would just be the sum of the electric field times the area around some surface, is equal to the enclosed charge over epsilon sub naught. Now, before we usually just express it like this, but then that's just, it's E dot A all the way around the surface. We did it for a sphere. For a magnetic field through a closed surface, because I don't have any monopoles, magnetic monopoles, whatever field I have going in, I have going out, unlike charges where I can have a charge enclosed. This would be zero. So Gauss's law of electricity, Gauss's law of magnetism. And now throw in Ampere's law, the sum through actually I'm gonna write out the sum around a full surface of B dot A is equal to 0. And then B dot delta L is equal to mu naught I. There are a set of 4 equations called Maxwell's equations. And if I haven't mentioned it before, I apologize if I have mentioned it before. Maxwell did not call them Maxwell's equations. Maxwell used that 3rd equation and a 4th equation we haven't gotten to yet and derived the speed of an electromagnetic wave. And we will go through that when we get there. But this is 2.5 or 2 2/3 of Maxwell's equations. Maxwell's contribution is that there's another term out here that Ampere did not have. Because we talk about current flowing in at any point in a circuit. Current flows in is also the current flows out. But if I have a parallel plate capacitor, I have current flowing onto the plate. I have current flowing off the other plate, but I got a gap in the middle. What's going on in that gap in the middle? If I have current flowing onto a plate, shouldn't I have something flowing off the plate? Maxwell accounts for that and then uses it. The great effectiveness to come up with a theoretical basis for light being an electromagnetic wave. We're not there yet. We definitely have to get the next equation before we can do that, but just sort of where Ampere's law falls in the scheme of things. So quick plug and chug. I have a wire. Let's make it a 5 ampere wire. And let's assume that the wire is long, a long wire. If I am 3 centimeters off of it, what's the strength of the magnetic field here?
The mu sub naught I over 2 pi 3.
We've got to be careful about units there.
Oh, is it, it's in centimeters, so 0.03.
All right, so what's the value of mu sub naught?
That's our permeability of free, is that the 8.85?
No, that's epsilon sub naught. That's permittivity.
Yeah. Ugh.
Surely I've written down what permeability of free spaces.
It's like a constant.
One of
Yeah.
the notes we introduced, I don't have a number.
Yeah, I don't know if you wrote, yeah, I don't have a number either.
I don't have.
We've just been dying to know, Dr. Fox.
Yeah.
4 pi times 10 to the negative 7 Tesla meters per ampere. That's the value of mu sub naught.
What was the part before the meters on the top?
Tesla meters,
Um,
Tesla times meters over amperes.
which is written the way torque is, right?
Tesla's got one.
Or like-
I can use more of a curve in my torque. I don't think tau is actually used for any unit, but
Wait,
times
does magnetic field have units, or am I totally spacing?
Teslas. Magnetic field is Tesla as the unit.
Okay,
That is a little funny.
That's not what it is.
so the units of B would be Tesla,
Yes,
okay.
which means that this M and A better be canceling out at some point, which they will. Divided by 2 pi times 0.03 meters. So the amperes cancel out, the meters cancel out, we're off to Tesla. And what is the magnetic field? Garrison, it looks like it's all down to you.
As it normally is, it's something I'm accustomed to, and something I embrace wholeheartedly. 3.33 times 10 to the negative fifth. Oh, alright, hang on. Teslas.
Yes.
Is it spelled like Tesla, like?
Yep.
Like the car?
Nikola. Or-
Except this definitely came before the car.
Yes, it is named after Nikola Tesla.
Nikola Tesla. Oh, Brooke, come on, you can't get.
Capitalism drove them into poverty, but at least we can honor them with a unit, so you should be happy about that, right?
In a car, I guess, so.
Alright, so that's just a straight up plug and jug. This is the infinite wire. There's one other case, and this is, well, you know, it is what it is. If I have a loop of wire with current flowing through it around this loop, the magnetic field at the center the magnitude of the magnetic field, we'll get into directions in just a moment, is mu naught times I over 2R. The pi does end up canceling out. Now, so for the infinite wire, we get mu naught I over 2 pi R. For the loop of wire, we get over 2R. The difference obviously is the number pi. Some students, they get in on the test and they go in, all right, I got a circle, circle's got a circumference of 2 pi r, so, let me use this one for this loop of wire, and so that one must be for the straight wire, and it doesn't work that way. The loop of wire does not have pi in it, the straight wire does. Because this is the circumference of the circle that we created. And I'm assuming plug and chug is not gonna be an issue for this group. Let's talk about direction of the magnetic field.
Before we move on, I'm
Okay.
having a hard time understanding conceptually what's happening with the loop of wire.
I got my wire right here, I have current running through it,
Yep.
and I wanna know the magnetic field in the very center.
Oh, okay. Gotcha. Thank you.
Alright, other questions? Alright, so the magnetic field that is created by a current, you'll be glad to know this is the right hand rule. I mean, we can pull it from this right here, but it ultimately comes down to, I got my thumb pointing in the direction of current flow.
Stand gun.
If you wanted to go stem gun works really nicely for a charged particle. When you're doing current, I think the hitchhiker works better.
No.
It all ends up the same. But if I got a current flowing like that, my fingers curl in the direction of the magnetic field. So, which means that up here, the magnetic field's coming out of the board. Down here, it's going into the board. My magnetic field is basically traveling, it's in a circle. So, it's coming out of the board up here, into the board, down here.
I'm sorry, I'm not understanding.
Oh,
The
wait,
direction of the current is the direction of the wire, which is this way.
Right?
But because they're electrons, it's this way, so I'm gonna use my left hand, because that makes more sense.
Okay.
So I'm gonna point. But then how do you know which way to curl your hand?
See, when we did the right hand rule before, when we did the spin gun, we had a magnetic field that we had a particle going through.
Right,
We're creating the magnetic field this time.
right.
So that's why we're sort of changing the way that works.
if you do the, like, what we used to do for torque, like, point your thumb in the direction of the current, then your, like, fingers, like, curl the way it's supposed to go, not automatically, but, like, it, like, goes into the board and,
But what if I
So-
point my thumb like that?
So if I have let's say this is the wire right here.
What if I point my thumb like that, Brooke?
If the current is flowing up this wire,
Uh-huh.
I put my thumb in the direction of the current flow, my fingers are in the direction of the magnetic field, which means the magnetic field is going on your side of the wire, it's going that way.
Okay,
Over on this side over here, it's coming towards me. On my side of the wire, it's heading towards the door. Over here, it's going like that. So the magnetic field is traveling in a
okay.
circle around like that,
I,
getting weaker the farther out you go.
right, okay. So hitchhiker's rule, put your thumb in the direction of the current,
Yep,
which is the opposite direction of the electrons. And then the direction
Correct.
your hands curl is the direction, which is why it's coming towards us, okay. Yeah, towards us on top of the wire,
and away from us at the bottom.
yeah, got it.
Harrison, you were having issues before.
I still don't understand why is it coming the opposite direction below the wire?
Because it's like it's traveling in like a circle. So like, if you're looking at it face on, it looks like the current is coming this way, and then it's going away. So it's like coming towards you, going away, cause it's like a circle.
Okay, and that's why, okay. Okay, yes.
You can just picture like arrows going in like a circle, like you'll see the tips of the arrows coming up over the wire, and then you'll see the feathers as they go away.
Yep.
Gotcha. Okay, yeah, that's what I was confused about when I manipulate my thumb.
Stay good
Why it was
visual
different.
right there.
Like this versus.
It should get the same. I mean, basically, I point my finger like that, the current's going this way on that side of the wire and then down. Or if I went like that, it's going down and,
Okay. Yes, okay. I understand.
all right. On the loop of wire, if my current is traveling, I guess that's counterclockwise. Well, at this point right here, I got my current's flowing like that, so the direction of my magnetic field, though it's going into the board out here, out of the board in here, so it's coming out of the board here and into the board here.
So it's like making a little circle around the entire loop.
Yep.
Yeah.
And so down here, out of the board, into the board, out of the board, into the board. Oops, those should be X's. Same over here. Hopefully you're sensing a pattern here.
I sense it.
So in which direction is the magnetic field traveling in the center?
Forward.
Yep. For those who are ready to handle it, for a loop of wire, if I curl my fingers in the direction of the current flow, the thumb points in the direction of the magnetic field in the middle. If you're not ready for that, you can just keep, go work your way around.
Wait, so now we're changing, instead of point your thumb in the direction,
Well,
Okay.
yeah, I was ready for that. I was already kind of doing that, and then you
Yeah.
said it, and I was like, oh my gosh, I'm a step
Makes
ahead.
it
My,
very
my idea came to fruition.
Because you were thinking it, because this is your dream.
This is.
All right. It's potentially a lot to take in right now, but some of you probably are already handling it, and you're just sitting back thinking, all right, I'm just waiting for everyone else to catch up like Harrison's doing right now.
Yes, yes.
I'm definitely a kinesthetic learner, but it's very confusing when the rules change. Like sometimes your fingers point in the direction of the charge that's being entered into the magnetic field, and the finger curl means one thing and the thumb means another thing, and other times you point the thumb. Like I think because the rules are changing, it's hard to.
Ultimately, it still comes down to this cross product. That if my current is flowing in that direction, so that's the direction of delta L, R is from that point is from where the current is to that point right there. So L cross R points out. At the heart of it, all of it, is the cross product in this formula and then the force formula, which I've erased. I think we're ready. I have two wires. Current flowing in the same direction. Call it I1 and I2. Assume these wires are long. Each wire will create a magnetic field that the other wire will sense. When a wire senses a magnetic field that's perpendicular to it, it will move one way or the other. So the question is, which way will these wires move? Not necessarily in the same direction.